Hey folks, I'm really excited to be doing this Starknet and Cairo 101 for our Basecamp with Foresight. So my name is Manmit Singh, and for those of you who are in college, we might actually not be that far apart in age. I only graduated with a degree in computer science last year, and when I was in college, I had the amazing opportunity to be able to do research, particularly in game theory and DeFi. After graduating, I worked briefly on a summer research fellowship in crypto, and then was lucky enough to be accepted in Starkware and then the Starknet Foundation to work as a developer advocate for the US. Today, I'm just going to be talking to you briefly about what Starknet is and what Cairo is and give you something to go off of for this journey that you're about to embark on. If you ever feel like you have any questions or you want to talk to me about anything, you can reach out to me on any of the socials provided at this link tree. So usually I do these talks in a much more interactive fashion, but since this is a recording, I have a few talking points that I'd like to go over. We'll be going over what blockchains are and why they're slow. We might even skip past what blockchains are, presuming some amount of knowledge on your part. Then we'll talk about layer 2s, rollups, and that's where Starknet really comes in. Finally, we'll talk about some of the issues and active areas of research for layer 2s. And how you can get involved in building the future of Starknet and blockchain. But before we start all of that, I'd like to talk to you about the blockchain paradox. So sometimes this is also expressed as the blockchain scaling trilemma. And what it means is that colloquially, or based on the existing literature around blockchains, people think that there are three features which a blockchain architecture cannot achieve simultaneously. These three features are decentralization, scale, and security. Though really, these are two features, because no matter what system you use, you always want it to be secure. So let's say it slightly differently. The blockchain paradox says that a blockchain's got to choose between being scalable and decentralized. And I suppose this difference is quite starkly highlighted in our existing banking and record-keeping infrastructure. When we use banks for storing financial data, or government offices or social media websites for storing personal data, we're essentially delegating accountability to store and process this data to a central party. But who we are really trusting is whoever is auditing the central party. In many cases, this would be the government. Blockchains provide a more global, cross-border approach to this by leveraging distributed digital networks and allowing people to run these things called nodes, where they can basically download and verify the state of the blockchain and have inclusive accountability. So you can think of it as like moving the responsibility to store and process the data, verify it with just one agent versus with several interested parties who can keep each other in check. Now, I assume that you're already familiar with these concepts, but I want to highlight here that this distributed accountability model or inclusive accountability model sacrifices scale, because this network has to be designed in such a way that multiple parties are able to download and validate the various transactions on the network within a short duration of time, which is also called the sync time. And that's really the biggest challenge that a lot of blockchains run into when they're trying to scale. Is it's almost like saying that the chain is as strong as the weakest link. So to some degree, blockchains have to account for a reasonable assumption of compute and memory on behalf of each node operator. Another thing is the word accountability itself. Blockchains like the proof of stake Ethereum model rely very heavily on the assumption that if someone breaks their game theoretic guarantees, the network can accurately identify that party, also sometimes called an adversarial agent in game theory. And in order to do this, a lot of blockchains like proof of stake Ethereum sacrifice the privacy of individual transactions. So that's that. Let's put a pin in this conversation and move on to this really exciting mathematical concept called validity proofs. Now, I want to be clear, validity proofs themselves don't really have much to do with blockchain. That's not where they were born. Validity proofs were first introduced as an academic idea by applied cryptographers in the late 1980s, kind of came to life in the 90s and 2000s, and the first industry applicable algorithms came out a little bit after 2011. But what's a validity proof? So skipping all the fancy and well, actually quite interesting stories, but just in the interest of brevity, I'll explain what the validity proof is. So imagine you are someone running a computer program and you have certain inputs and a certain algorithm, and you're running it locally on your computer. For the purposes of this analogy, we'll call you the prover. And then let's assume that I, in this case, want to make sure that you actually ran this program correctly based on the inputs and the algorithm that you're claiming to have. So I can be called the verifier. What a validity proof is doing is it's allowing you, as someone who's running the computer program, to convince me by using a small computational object called a proof that you actually ran this program correctly, given the inputs and the claims you made about the algorithm. The alternative to having the proof object would be rather inefficient. You'd have to send me all the inputs and the algorithm and the result, and I would have to use my computer, taking up time and, of course, computational resources, to rerun the entire algorithm with those inputs and compare our answers. But sometimes when the algorithm is simply too big or the inputs are too varied or you want to preserve their privacy, you don't want to go through that naive route. You want to go through a proof. And so I suppose the catchy way of saying this is proofs enforce the idea that provers do the right thing even when no one is looking. There are various types of constructs or various types of styles of proofs, including rank 1 constraint system proofs, Plonkish proofs, and Stark proofs. We'll be zooming in a little bit more on Stark proofs, but for the moment, I want to go over some of the important properties of a validity proof. So the first two are really just the same thing. They are saying that if you're an honest prover, that is to say, you're someone running the computer program, you're an honest prover, you'll always be able to convince an honest verifier and never be able to fool an honest verifier if you're dishonest. So it's kind of coming at the same guarantee of safety from two different angles. And then lastly, as you can see that, we've basically created a situation where the prover is giving a small computational object to the verifier. This can allow the prover to do various things. For instance, the prover could obfuscate, which is to say that they could, hide some of the inputs or some of the details about the algorithm and still create a proof which can sufficiently satisfy the verifier. And this is called zero knowledge. Basically, the idea here is that the verifier, the prover, is able to create such a proof which can convince the verifier that they ran the computer program correctly, but the verifier doesn't get to know certain inputs or algorithmic details which the prover doesn't want them to know through the means of cryptography. Now, one thing that I'll note is that when I say always and never, I want to be very clear that this is all applied cryptography. And applied cryptography is probabilistic in nature, which means that always equals something that's extremely probable, and never isn't just never, it means something that is extremely improbable. So as I said, we'll be focusing a bit on Stark proofs. Brownie points for anyone over here who knows what Stark means or stands for. But I think the way it's named is actually quite brilliant because it explains what the proof itself is. So Stark stands for scalable, transparent, argument of knowledge. All three words tell you something about what this is. Scalable. What that means is that Stark proofs are constructed by using lean cryptographic methods, which is to say that executing the cryptographic functions that make a Stark proof is very easy for a computer. And that makes the proving time or the proving overhead for a Stark proof quite low. Or in other terms, if you're the prover, you're running your computer program, you can generate a Stark proof very easily. Transparent. What that means is that since you're depending on certain lean cryptographic methods, such as collision-resistant hash functions, you're not really worried that if some detail about the proof generation gets leaked, someone else can recreate a false proof and collapse the whole system. So there's no trusted setup in the generation of a Stark proof. And then finally, argument of knowledge. Now, argument of knowledge goes back to my claim in the previous slide that all applied cryptography is probabilistic in nature. Because what an argument of knowledge means is that this proof holds against a computationally bounded adversary and a computationally bounded verifier. That is, say, the proof is designed so a computationally bounded verifier can verify it, and it's safe against a reasonably computationally bounded adversary. Now, I know that a lot of conferences and a bunch of talks about rollups often use the word ZK. But as we spoke about in the previous slide, zero knowledge is an optional property of a validity proof, not a required property. And at least at Starknet, because that's the context in which we're speaking, we use Stark proofs, not ZK Stark proofs, which is to say in nature. Because what an argument of knowledge means is that this proof holds against a computationally bounded verifier. That is, say, the proof is designed so a computationally bounded verifier can verify it, and it's safe against a computationally bounded adversary. Now, I know that a lot of conferences and a bunch of talks about rollups often use the word ZK. But as we spoke about in the previous slide, zero knowledge is an optional property of a validity proof, not a required property. And at least at Starknet, because that's the context in which we're speaking, Stark proofs, not ZK Stark proofs, which is to say that we prove statements, Stark proofs, but we don't obfuscate any information about the underlying computation. I want to go over the differences between Starks, which is a popular construction of proofs, versus Snarks, which is another very popular construction. Basically, as I mentioned, the proving time Stark proof is really fast because you're using lean cryptographic methods. But this also means as opposed to a Snark. And because of that, the verification Stark proof tends to be a little higher in the sense that it grows polylogarithmically in the size of the proof itself, whereas a Snark proof is constant to verify because it's constant sized. And as far as trusted setup goes, we covered that Starks don't use trusted setup, whereas Snarks do. And theoretically, if we assume I suppose the adversarial model where we're not just dealing with bit-based computers, but qubit-based computers with orders of magnitude more computational ability, Stark proofs would still be secure against such adversarial models. So now we've spoken about validity proofs, and we've talked about the scaling trilemma. Let's put these two ideas together to tackle a problem that's been relevant in the blockchain world for a few years, which is a problem of scaling Ethereum. Now, there are two problems really over here when we say scaling. First, we already spoke about, which is distributed verification. Everyone who runs a full node on Ethereum has to download all of the transactions that have taken place on Ethereum and have been put in blocks since this. And they have to maintain the state of the network fully, which are relatively high memory requirements, but it's also time intensive because to sync and crash can take quite a bit of time. The other thing is block size. So Ethereum has a fixed size of blocks, and each block can only hold so many standard Ethereum transactions. So as Ethereum grows in size, over time, each run will have to wait longer and longer and longer to find an empty block to get into. You can also think of this as being in a really congested part of town and trying to get a taxi. And the taxi may take a little longer. For instance, you do Uber or Lyft, and they'll just say, we can't find you people because it's so busy. And if you go to a more isolated part of town, you get the Uber very quickly. So the way we apply validity proofs to scaling Ethereum is that we basically allow a larger and stronger computer, or perhaps just to specialized efficient computational, we collect users' transactions and validate them and provide them to the rest of the network in a more format, so that the network can put this compressed form of these transactions into a block and save space. Also provide, or I should say, the centralized efficient computer validators with a stark proof that this new state, which it has computed based on these new transactions, is actually valid. And so the validators can be, which represents all of these transactions, is actually a correct representation. So you can see how a centralized, or a set of smaller, of centralized, more basically do the heavy lifting of syncing with the chain and sequencing and new transactions without having to bother all of the other validators. So one question might be, well, how does Starknet do this? So for those of you who've looked at, some other popular validity proof libraries out there, you might have looked into Socrates and Circom, the same concept, which is that they want you to express your computational logic as a circuit, and that circuit is then mapped to a polynomial and turned into a proof. I won't go into that because this is not a math-related lecture. But what you're essentially doing is expressing your program as a circuit. Now, for most people who have a computer, we're not used to expressing computations as circuits, but expressing them as programs, step-by-step logical programs that execute on a traditional von Neumann CPU architecture and model. And so Cairo, which stands for CPU for application, essentially allows people like you and I to write traditional-looking computer in a language which is very much like Rust, and to assume a von Neumann architecture in a RAM-based memory model, write these programs, and then Cairo, which is a virtual machine, compiles these programs into an underlying form which is provable. So essentially, it abstracts away its own backend and allows you to write provable programs, not as circuits, but as normal computer programs. And further, Cairo VM's execution can be. Now, I just want to put this slide out there to help you get a better mental picture of how efficient this is. We spoke the naive way of verifying a transaction versus verifying a set of transactions by using starks. You see on this plot that as the number of transactions grows, the polylogarithmic plot is significantly lower and lower compared to the linear one, which would be to say, for instance, rerun transaction. So in a way, validity proofs are to computation on chain what zip files are to file sites. For instance, if you're ever attaching a file to an email. Blockchain scaling. Validity proofs are used to scale blockchains. Let's talk about the type of product, class of product that this validity solution has produced. It's often called a rollup or the layer 2. But before we talk about layer 2s, I'd like to have some formal understanding of what the word layer means. So as for Vitalik, a layer is a blockchain which provides ability to another blockchain. So if you're calling the blockchain it's scaling, will be called the parent chain. And who does this by essentially collecting transactions and then validating and submitting them to the underlying for ordering and blockifying them. This alleviates the burden of having to validate transactions from the parent chain itself. And the parent chain can be because of the proof that the layer 2 said one. But the way that you can think layer accepts transactions from you, and those transactions achieve finality on another blockchain that would be the roll up on that other layer. So you could have a layer 1, layer 2, layer 3, and they all keep settling on the layer beneath them. So that's essentially the whole model over here. I suppose this diagram kind of summary so far is that you have a big computer generating proof and various smaller computers with much lower computational and memory requirements being able to verify it. So this part of well, what exactly is Starknet and what it does. The next part is a little bit more about what people are doing with Starknet. And we'll start with some of the open research questions. So let's go over the security guarantees for a rollup. The literature on rollups, there are 3 main security guarantees: data availability, safe transitions, and censorship resistance. I ran out of slide space, so I just said censorship less. Data availability is saying that for a rollup to be truly safe, it needs to blockchain. That would mean that the layer you submitted to is a rollup on that other layer. So you could have a layer 1, layer 3, and they all keep settling on the layer beneath them. So that's essentially the whole model over here. I suppose this diagram kind of sums the entire story so far quite concisely, which is a big computer generating proof and various smaller computers with much lower computational and memory requirements being able to. So I guess that concludes this part of well, what exactly is Starknet and what is the next part is a little bit more about what people are doing with Starknet. And we'll start with some of the open research questions. So let's go over the security guarantees for a rollup. As per the literature on rollups, there are 3 main security: data availability, safe transitions, and censorship resistance. I ran out of slide space, so I just said censorship less. Data availability is saying that for a rollup to be truly safe, it needs to provide enough of its state information to the parent chain so that if the rollup ever stops working properly, pick up that state that is stored on the pin and recreate the. And this way, if you had money or it's not lost if the rollup stops working or if the original operator stopped running, the ability to rerun and recreate your state. The second is safe transitions, meaning that if the state of the rollup is being moved from one to another based on a batch of transactions, how do we know that these statements based on the transaction that is accepting are indeed, which is really to say, how do we know that the rollup isn't just accepting, validating wrong transactions? Now, I'm not sure of this because we're using not just any big guarantee or any state guarantee, but we're using a cold mathematical proof that the transitions are correct. Finally, censorship resistance. Now, what this is saying is, okay, anyone can up on Ethereum. Can anyone put a transaction up on a rollup? And ideally, for a rollup should be as censorship resistant as its parent chain in order to be reasonably censorship resistant. Now, one way to deal with this is if a rollup is making its state available on the layer 1 parent chain and has a contract on the parent chain, a user can always call the bridge contract on the parent chain and make their transaction themselves, even if the nodes on the parent chain on the rollup aren't accepting their transactions. But this is really research, and Starknet is also researching. I really don't have the time to go over this in detail here, or this will become an entire presentation about decentralized sequencing and proving. But you can look at the detailed proposal for Starknet's decentralization at this link. We welcome your feedback. So far we talked about the research related stuff. Now let's talk about why people are so excited about Starknet. We'll start with the most obvious suspect, which is cheap computation. Basically, now you can submit more transactions, or how should I say, you can include transactions in an Ethereum block for cheaper through Starknet than you would have by interacting directly with Ethereum. And this allows you to do things like building more complex DeFi smart contracts, building autonomous worlds with NFTs. And there's actually some great projects like the Starknet, which is a tool chain autonomous worlds, as well as really cool games, really like Shoshin, which I've linked over here, really appreciate the complex, the computational power that Starknet brings to users. Let's talk about account abstraction. Abstraction is not at all a Starknet only thing. It just means that you're able to write your own account as a smart contract as opposed to having to receive one out of the box and not being able to change it. This allows you to create accounts which can do much more flexible, complicated things than accounts on Ethereum have been able to do in the past. Like you could just, off the bat, make a multi-signature account or a multi-signature wallet without having to go through a third-party provider to outsource that work. You can do it yourself. You can also do something that's particularly close to my heart, which is you can use a phone in a cold wallet. Most phones today have a called a secure enclave, which is essentially an entire CPU that's cut off from the system you use when you're actually running the applications on your smartphone. And usually these secure enclaves implement a variety of signature schemes that aren't traditionally supported on blockchains. And so you can see, for instance, one of the signature schemes for Apple's phones is written over here. And this scheme isn't traditionally supported on Ethereum, but with Starknet, because Starknet supports account abstraction natively, meaning all accounts are account, which can verify the signature that is written by your phone. And in doing so, you can essentially turn your phone into a hardware wallet, which can then be used to sign transactions in a much more intuitive and user-friendly way. And also this bridging, which again is not just a Starknet only thing, but it's something that the field of do. So right now, if we assume that there are these chain A and chain B, and you're a user on chain A, you want to send a message to chain B, the way that generally works is you'll get that message published on chain A. Then people who are running nodes on chain A, well, of course, get the update and they'll get your transaction, pick it up from the mempool or whatever the architecture is. It's finalized a subset of these attestation committee or attestation subset attest that this transaction is actually correct on chain A and provide that attestation to chain B so that chain B can then and be assured on chain A. Using validity proofs, you're actually able to eliminate the network altogether, and by doing so, eliminate a source of centralization. Because now chain A and chain B can effectively run light client nodes on each other and observe the transactions or the state updates on the other chain and verify them by using validity proofs. If you want to learn more about storage proofs and how they enable trustless bridges, there is an absolutely amazing project that's called Herodotus, and I highly recommend it. This is also an application set that is particularly close to my heart because coming from a DeFi research background, we learned that one of the biggest problems of the roll-up oriented roadmap for Ethereum is the allocation of liquidity. And very efficient and secure bridging goes a long way toward that. Finally, something that's exciting to almost everyone in this market right now is verifiable big data. So I guess the most intuitive way to think about this is if you use OpenAI's ChatGPT. Currently, there are two you can choose from. There's 3.5 and GPT-4. 3.5 is free, whereas 4 is with a monthly subscription. Now, if you ask, so say for instance, you're someone who's paid for that model, and you go up to the website and you make a query, like, at the beach or whatever. When you receive the response, as a user, how do you tell for sure that you got it from GPT-4, 3.5, how do you even know that they're different? Now, I'm not trying to insinuate that OpenAI's models aren't or that do not provide the services that they claim to be providing, but in an on-chain environment where the motto of the user base is verify, don't trust, you want an ML model that you're using, is actually inputs and certain weights of the model. Now, this is arguably the single most active area of research, at least where I live in the blockchain space, which is here in the Bay Area. And I highly, we have an amazing project on ZKML, and it's called Giza. And you can visit their website and watch their tutorials. In one of them, they teach you how to build a neural network that can be proven in like less than 15 or 20 minutes. And that's pretty. And then finally, we talk about fractal scaling. So remember how layer 1s, 2s, 3s, da 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 da. Well, essentially, why would you ever want to go one layer 2, right? So if you have a layer 1, you have a layer 2 that collects all these transactions, validates them, blocks them up in little spaces, and then provides them to layer 1 for finality. Why would you ever 3 on top of the layer 2? Because intuitively, if you think about it, the layer 3, if it works in exactly the same way, won't provide you any scaling, but would still depend on the ability to settle those transactions before going to layer 1. But the idea is that beyond layer 2, we actually start building not general, but highly optimized application-specific chains. And if you really think about it, building application-specific chains which cut wherever they can and are extremely optimized for a certain use case can achieve a much higher throughput than a layer 2 and can be designed in such a way that they enable much more frictionless user experiences than working directly with. And so we recommend that you take a look at the very, very famous and one of our favorite projects in the Starknet ecosystem, which is